Good evening, everyone. Welcome to the third session of Step to IoT, a webinar series on the Internet of Things organized by IET on campus, University of Peradeniya. Throughout this series, we have been improving our knowledge on IoT, starting from the very basics, such as the definition of IoT, the differences between IoT and the Internet, and machine-to-machine devices. In last week's session, we talked about a typical IoT architecture and its components, as well as IoT reference models. Now, in today's session, we are going to take a step further and talk about the physical design of IoT, devices and endpoints, and also IoT communication models, protocols, and APIs. If you're joining us today for the very first time, let me introduce the guest speakers of this webinar series, Mr. Anuradha Udunuwara and Mr. Rajiv Weragama. Engineer Anuradha Udunuwara is a senior enterprise solutions architect at Sri Lanka Telecom with more than 17 years of experience in the industry. He graduated from the Faculty of Engineering of University of Peradeniya with a bachelor's degree in electrical and electronics engineering. He is the world's first MEF Network expert with many other related achievements. Moving on to Engineer Rajiv Weragama, he is a senior engineer at Sri Lanka Telecom with more than 12 years of experience in the industry. He has a bachelor's degree as well as a master's degree in electrical and electronics engineering. And he's currently pursuing a PhD on the Internet of Things at the University of Peradeniya. Apart from being engineers at SLT, both of these individuals are researchers, trainers, as well as well-known speakers at Commonwealth telecommunication organizations. Now, without further ado, I cordially invite Mr. Weragama and Mr. Udunuwara to start today's session.
Thank you, Siri. I hope all of you can see my screen, right?
Yes, sir.
Okay, then. Good evening to all of you. And as Isuri clearly mentioned, today is the third day of Step 2 IoT webinar series. So we will discuss more on physical design, devices, and endpoints in the first session. Before moving on to the physical design, let's see the architecture of a typical computer. It should be noted that this architecture is common to almost all computers running today, from the smallest industrial controller to the largest, you would say, the supercomputer. What sets the larger computers or a supercomputer which is capable of executing trillions of floating point operations per second is that they are built from a large number of processors and memory modules that communicate and work cooperatively on a problem. The basic architecture is almost same. So the basic computers have four major components: the central processing unit or the CPU, we simply call it the processor, the memory, input-output devices, and one or more bus structures to allow the other three components to communicate with each other. There are a large number of I/O devices which can be connected to a computer, which are used for different functions. Their applications, appearance, the data rates, and other characteristics differ from each other. The next thing is an embedded computer. So the embedded computers can be seen in everywhere. They are in our phones, microwave ovens, and also in airplanes, automobiles, and even in a calculator. The list goes on and on. And an embedded computer, which is an integral computer or the integral component, I would rather say, of most embedded systems. It is a combination of hardware and software that is designated to perform a highly specific function, not a general purpose function. For example, the type of embedded computer in a washing machine will not be the same as the embedded computer which you would find in a camera. The IoT devices are somewhat similar to an embedded computer. Now let's see what is the IoT technology stack. By breaking down a full IoT solution into these 5 layers, we can better understand and analyze the business as well as the technology trade-offs that are needed at each level and in the system as a whole. When you are designing something in IoT, we need to have all these essentials: the device hardware, device software, communications technology, cloud platform, and the cloud applications. Out of these 5 layers, the first 3 layers are often related to the device level. Now, let's see what are the building blocks of IoT device hardware. Regardless of its application, all IoT devices share some similarities, or we call them the building blocks, as shown in this figure. This block diagram simplifies the composition of IoT hardware using these 4 blocks: the thing, data acquisition module, data processing module, and the communication module. If we focus on the first block, that is the thing, the devices constitute the things in the Internet of Things domain. So devices act as the interface between the physical and the digital worlds. They are the first layer of IoT technology stack. In many IoT products, the thing is fully integrated into the device. Just think of a smart device or any kind of an autonomous vehicle which is capable of monitoring and controlling themselves. In such a scenario, all 4 building blocks are bundled together and integrated within that so-called thing. Simply, let's say that we are selling some kind of a product which has an integrated thermostat to measure the temperature of that particular device. So our IoT product will be the part which has that thermostat, but it is connected to or maybe embedded in the product we are selling. So we would rather say it is a greenfield solution. That means we make the both the IoT device as well as the thing which uses our IoT device. The next particular device is shown in this block diagram. So just think of any other asset. I would rather call it a non-smart or a dumb device, which you want to make it a smart device. In that case, we can connect the rest of the 3 modules to this dumb device, and together those 3 modules we can create a smart device. For an example, you can develop a device which is capable of adding sensors and communications to a wind turbine. In that case, you are not selling the wind turbine, but the but just the device that connects to the wind turbine. In other words, the wind turbine example is a brownfield solution. So you are not selling the thing which you want to make smart, but the modules which will make that thing smart. So the second block is the data acquisition module. The data acquisition module focuses on acquiring physical signals from the thing and converting them into digital signals that can be manipulated by a computer. So we discussed more on DAS system in our previous lesson. So when designing a device, you have to answer 4 questions related to the data acquisition module. First thing is, what sort of physical signal are we going to measure? That means uh, what kind of data or signal are we going to collect? It can be a temperature related signal or humidity or vibration or something else. The second question is, how many sensors of each type do we need? Are we going to deploy only one particular sensor or multiple sensors? The third thing is, how fast should I measure the real world signal? Are we going to send the data at real time, or are we going to store it for a particular period of time and then communicate? Or are we going to take the measurements uh, from, I mean, one particular time within a particular minute, and then we stop taking that signal or measuring that particular signal and again measure it after certain period of time. And the final thing is, how much accuracy do I need in my measurement? That is the accuracy of measurement. So in other words, we could say it the resolution of the measurement. The answers to these questions will inform the requirements for our data acquisition module, as well as it will give us an idea of how much data our device will produce when it is deployed. Now, the third block is the data processing module. And this is the computer that processes the data, performs local analytics, and it may store data locally, and it might perform any other computing operations at the edge. So when deciding the processing power of our device, we have to consider how many sensors are we going to connect to our device, and does it require real-time processing, and also are we going to do some sort of analytics at the edge, and what are the size constraints? So if you are going to embed this device into a small thing, then we have to reduce the size of our uh, smart device as well. And finally, do we need to keep any provisions for the future upgrades? If it is yes, then our design has to be changed accordingly. And when it comes to the storage, we have to answer these questions. How much data are we going to acquire? And what is the rate of acquiring data? And how much data are we going to send to the uh, central node or towards the cloud? And how often are we going to send data? That is the frequency. And how long are we going to retain data within that particular device? Based on that, we can come to a decision, or we can make a decision of the storage requirement of our device. And the final or the fourth block is the communications module. So this is the circuitry that enables communication with the cloud platform and with any third-party system, either located locally or in the cloud. This module may include communication ports such as USB, serial, or any other communication port related to PAN, LAN, MAN, or WAN networks we discussed last week. And also, it may have any interface to support the wireless technologies belongs to any of these wireless technologies mentioned in this figure, starting from a short range or the what we call the near field communication or Bluetooth technology to a interplanetary network. The communications module can be included in the same device as our other modules. So it could be a separate device that is specifically for communication. This approach is often called as the gateway architecture. And this is the generic block diagram of an IoT device. It really is a sort of an embedded computer, even though these devices are often small in size. And also, these devices are having a lesser computing power. And even though their power is somewhat lower, they fulfill the criteria of becoming an embedded computer. As you can see in this diagram, it has a processor in the form of a microcontroller and memory, local storage, I/O interfaces, wired or wireless connectivity, and sometimes you may find a graphics processing unit or a GPU as well. IoT devices collect data from onboard or attached sensors. You are totally aware of that. And the sensed data communicated to another device or each IT system or even to the cloud through the gateway. And we have discussed the possible technologies in our previous session. These sensors and actuators will be connected via the I/O interfaces mentioned in this diagram. And in fact, the sensors are the input devices and actuators will be the output devices. Now, what is an endpoint? As per GSMA, the endpoint is defined as a physical computing device that performs a function or a task as a part of an internet connected product or service. So that is the definition of endpoint. Now let's see what sort of configurations can we have in our IoT networks. As per GSMA, there are 3 different IoT endpoints. If you see IoT endpoint configuration number 3, the lightweight endpoint configuration, it is typically a sensor or simply a physical device, such as a light switch or a door lock that has few functions. Its goal is to serve a single physical purpose and to provide metrics to the service ecosystem or to the computer. It commonly uses a very cheap processing unit or a low power processing unit, possibly an 8-bit microcontroller, and a short distance short distance personal area network for the connectivity, and that can be either in the form of uh, low energy Bluetooth solution or a Zigbee connectivity. Those are two examples for that connectivity solution. And the examples of lightweight endpoints are the home security sensor systems, proximity beacons, and also the wearables we use in our day-to-day lives. It includes the smartwatches and pulse meters and so on. So due to the low cost of lightweight endpoints, the security technologies available to these devices are minimal. Security technologies that require a significant amount of current draw, cost, or even the space on the circuit board are not usually available in these systems. However, lightweight endpoints can still use cost-effective and small trust anchors to implement robust security frameworks in these devices. And the configuration type 1 and 2 both related to the complex endpoint configuration. This endpoint model typically has a persistent connection to a backend server over a long distance communication link, uh, such as cellular uh, connectivity, as shown in configuration number 1, or it can be connected using a Wi-Fi or Ethernet through a customer premises equipment or a gateway, as shown in configuration number 2. The device may also have a basic processor in it. Sometimes it can also be an 8-bit microcontroller, but is capable of running more robust processing, as it is either directly connected to an AC power source or it contains some kind of a battery and has regular access to battery recharging system. So there's no limitations in power side. And examples of complex endpoints are the IoT connected lighting systems, appliances such as refrigerators or washing machines, industrial control systems, we call them the SCADA systems, and cellular connected cars, tracking and monitoring devices. So the complex endpoints are capable of more current draw, typically implemented with more robust process, and has more space on their circuit boards compared to the lightweight endpoints, and these are enriched with more uh, security technologies, and as a result, much more can be done with these complex endpoints. So before sum up the first session, I would like to highlight one of the most important things happened in this week. The Mars Perseverance rover was landed on Mars on 18th of February. That means 2 days ago. And now you would be thinking that why is it relevant to us? In fact, it is a thing full of sensors and actuators, or I would rather say it is a network of things. It is equipped with multiple cameras, audio recorders, and many more special equipment. As per the IEEE spectrum, the Perseverance rover is bringing 7 science instruments to Mars, including a camera system called Mastcam EZ, which is a zoomable panoramic camera. And there is another camera called SuperCam. It is a combination of cameras which are capable of detecting rock vaporing lasers. And there's another one called Sherlock. It's an ultraviolet spectrometer. And there are so many things included in that rover. And also, it has a sample catching system or sample. It collects samples from the mass surface. And also, this rover will control a drone called the Ingenuity, which is a robotic rotorcraft that is planned to be used to test the technology to scout targets of interest on the surface of Mars. And the captured data will be used to find the best driving route for future Mars rovers. So if you look at the broader picture, the Mars Perseverance rover controls the drone, and it probably uses some kind of a mid-range wireless technology to communicate with the drone. Also, it controls the things attached to it. So I told you that I consider it as a network of things. And the rover communicates with the Earth, and it is controlled by the NASA crew using interplanetary communication link. So this is one of the greatest and complex inventions and a crucial milestone in the practical implementation of IoT. So you can study more on this, as it will be useful to all of you in your future studies. So that's the end of the first session. So I will hand it over to my colleague Anuradha Udunuwara to continue the second session. Anuradha?
Thanks, Rajiv. Hope you all can hear me.
Yeah.
Yes, let me share my slides. I think, Rajiv, you have to stop sharing, right? Yes. Okay, thanks. Hope you can see my slides.
Yes.
Oh, yes. Thank you. Okay, so my topic today, as already communicated, is on IoT communication models, protocols, and APIs. So let's get started. Now, before we start, I think with respect to the IoT definition, we had a lot of discussions, I think, in all previous sessions. And I came across this while I was preparing the set of slides for this particular session. And this is from the Internet Society. And I just thought of sharing it with you, not to add another definition to the list of definitions that has already been shared, but just to point out the fact that there is no single universal definition, which is also mentioned by the Internet Society. And this is their way of defining IoT if you want, right? So that is the whole purpose of sharing it. But the key points, we have seen it many definitions: network connectivity, computing capability, and sensors, which are not everyday items, right? Normally considered as computers. And they generate, exchange, and consume data with minimal human intervention. So it's more or less resembles to what we have already learned, or maybe what we all agree. So with regard to the communication models, so sometimes we can use the term pattern. This whole idea of the communication models or the patterns that are possible with IoT devices is actually coming out of one of the RFCs, which is a request for comment from IETF, Internet Engineering Task Force, 7452, which is titled as Architectural Considerations in Smart Object Networking. So there you find these four patterns. One is D to D, device to device, D to C, device to cloud, D to G, device to the gateway, and also the last one, backend data sharing. So these are the four patterns or the models that we often see in IoT communications. And I think it's important, if you learn about IoT, like the many other things that has already been shared, to have some basic understanding about what these communication models are and how they differ from each other. And one important thing is that there is no hard and fast rule that you have to use one particular model. If you want in your solution or in your product or in your application, you can use multiple models or patterns. And also the usage of these patterns or models is largely influenced by the open versus proprietary nature. As you know, not only in telecommunication, not only in ICTs, we are talking about basically two ways of doing things. One is being open, inviting other ecosystem players to come and integrate with your systems and applications. The other one is proprietary, where you are the only person or the device that is communicating, basically blocking the others interacting or interworking with you. So same thing can happen in all these four models. The first one is called device to device. So it is more or less machine to machine. In this example, what you see below is from the Internet Society document, which is where the source is given. And what you see on top from the RFC itself. And those who read RFCs know that in IETF RFCs, you don't get colorful diagrams like what you see below, but rather everything done on ASCII. And it's not very much human readable, but it's a very good source of direct information if you are comfortable in sort of grasping what is mentioned in the RFC. So D to D, for example, is from, let's say, a light bulb to a light switch using a wireless network. In this case, examples like Rajiv also mentioned Bluetooth, Zigbee type of examples. There's no cloud involvement. There's no internet involvement. Just achieving some of the smart, these days we hear a lot of smart things like smart home applications, etc. So this is a very simple, smart light bulb controlling example. The second one is device to cloud. As you can see here, the devices are not directly connected. So devices are connecting to an application service provider. It could be something on the internet provided by a cloud player, or it could be something provided by a service provider. So, but you don't have a direct connection between devices. The devices are connected to the cloud. And there you use multiple protocols. For example, constrained application protocol is one of the widely used protocols for constrained devices, which is also defined in RFC 7252. And then we have datacom transport layer security and also transport layer security to achieve security needed for the device communication. You don't see much of security implementation in the case of D2D because it is close proximity communication often. So it is, you can have, but in this case of device to cloud type of communication, your transport layer security is very important. And below that, if you can remember your TCP IP stack knowledge or the ISO SI stack knowledge, you know that then you have your real transport layer protocols like TCP or UDP, and then your network layer protocols like IP. So the rest is not shown here. This is what is meant by D2C type of a communication. And then we have something called D2G, which I think most of you already know, is rather than device directly communicating with the cloud hosted server or an application environment, the device communicates with a local gateway. Gateways are always local in the context of IoT. So you get connected as a device to the closest gateway, and then the gateway actually communicates with the application hosted server using IP protocol. So you have different layer 1 protocols if you want, like it could be Bluetooth Smart, or it could be Wi-Fi 802.11, Wi-Fi 802.15, low rate wireless personal area networks, any layer 2 network. These are some of the examples. And then again, you build the same stack that you would build in any sort of communication protocol stack, like your IP. It could be IP version 4, version 6, then your transport layer, security if you want, and then high-level protocols like the one shown here. HTTP could be a high-level protocol, the application layer protocol, or COAP. These are the type of protocols that we use. So the primary idea behind having a local gateway is to allow the proprietary devices to communicate without an issue. So even though you are a proprietary device, if you use the basic communication protocols to a local gateway, and then local gateway sort of acts as the proxy or the translator between your proprietary communication protocols to the one that is most accepted by the service providers or the hosted cloud-based control platform or your application platform. And the last one, though it is also listed as a pattern or a model, it is more of a way of sharing data, backend data sharing example, which is, as you can see, is how you sort of share your information. Because if you follow this whole series of webinars that we have been doing, from the day one, you understand that IoT has a lot to do, especially these days, rather than on the devices, but on the data that the devices collect, generate, right? So it may not be a fair statement, but I would anyway say it because you have a lot of emphasis on the type of data that you collect and how you sort of use that data. Right? It was earlier mentioned, I think in one of the previous sessions, that data is the new oil, which is true because irrespective of how you collect it, the data has a lot of potential in delivering the outcomes that you would sort of require in these days. So there you have these provider-to-provider type of communication that enables users to export and analyze smart objects from cloud services. These days, you have a lot of cloud services, a lot of IoT cloud platforms. You don't have to build everything from scratch. It's just a matter of having the right interfaces and protocols and the right APIs. You can use a public cloud, for example, Amazon Web Services, or Google Cloud, or Azure, or Tencent, or somebody else's public cloud infrastructure to analyze your collected data. There are a lot of analyzing engines available. If you want high performance computing, whether it is process intensive or memory intensive or combined intensive, you can still have that. And you can sort of process any amount of data these days using the public cloud available resources. So two of the widely used protocols again is COAP and HTTP, and this is what is mentioned in the ISO Internet Society document and also in the RFC. So that is those are the models or the patterns that you can have for IoT communication. Basically, looking at the point of a device. And then if you look at the type of protocols available, I think this is, I was actually looking for a better diagram, but this is the best I could find, and it is one of the research papers on Internet of Things. I have given the link. So this shows from the physical layer going up to the data link, network, transport, and application, basically the TCP/IP stack type of layers, and then the type of protocols that you use in Internet of Things. So for example, I have not tried to sort of explain all the protocols involved, but a few things that we often hear, something like long range physical layer communication, and then GSM extended coverage, and then enhanced machine type communication. We have massive machine type communication in 5G, but we have something called enhanced machine type communication and narrowband IoT, which Rajiv is going to discuss at length, I guess, in the next session. And then you have Wi-Fi, then you have other type of protocols, near field communication, radio frequency, identity, etc. at your physical and data link. One of the things that you would notice is that the protocols for physical and data link are always shown combined, because you really don't have physical layer protocols as such. Physical layer is actually how you transport your bits and bytes, but basically the signals, the voltage levels, currents, and the very, very physical nature of communications, whether it is electrical signals or light signals in the case of optical communication, whether it is guided or unguided optical communication, or it could be pure wireless communication, where we find in most of the cases. And then you have data link layer, but in most of these things, you find data link layer and the physical layer combined, and the protocols are defined in that way. And on the network layer, if you carefully see, it's basically IP version 4 and IP version 6. And then on the transport layer, it is UDP and TCP. And then we have application layer protocols, for example, HTTP, and also MQTT, which is one of the widely used application layer protocols, MQ telemetry transport. And then there are certain proprietary things as well, because this diagram is done by somebody who has done a research. So this is one sort of a collective representation of all the protocols possible, irrespective whether it is open or proprietary. So he or she has included AND 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 plus, which are proprietary multicast wireless sensor network technologies or protocols. And there are certain protocols which are actually, for example, Bluetooth Low Energy is actually having its representation at all layers, like, for example, Z wave and wireless HART, etc. So their protocol working happens across multiple layers. So this is an example of how MQTT works, and there are a few keywords, which is publish and subscribe. So you have MQTT client. So the publisher is a temperature sensor. And then you have MQTT broker in between, which does the translation. And then you have to subscribe to a topic. For example, here the publish to topic is temperature. Then subscribe to topic is again temperature, and here the same. And then these are the clients of the same information. So you have clients on this side, which are the sensor side, and also your clients like the application side, or it could be a backend where you just collect the information and do further processing. So we discussed about the communication models or the patterns, and also the protocols, and try to bring protocols and interfaces. Like we often hear protocols and interfaces into context. It can be, this may not be the best example, but it could be something like this. if you go for an interview, there is a protocol for an interview. Maybe the protocol could be the way you should dress, the way the things that you should carry, the way you should speak, and certain body languages, body gestures, etc. That is protocol for an interview. So protocol is basically set of rules or set of agreements that that devices or people would follow in a certain situation. And for example, in this case, the person's eyes, mouth, and maybe all the 5 sensors could be considered as interfaces. So these are the ones actually do the communication. So you can communicate with eyes, you can communicate with mouth, you can even use your hands to do communication. So that's basically the elements of communication. So these are the interfaces. So that is one of the simple ways that you can explain the protocol and interfaces. But if you go into the space of IoT, but not necessarily IoT, but in the space of communication, you have basically interfaces identified in terms of physical and virtual, right? You can see, I think I have one slide from the IoT document where the interfaces could be physical and also virtual. Physical interfaces, like for example, F connector for a cable modem, or your RJ45 or RJ11 jack, or whatever the physical interfaces that you can feel and touch. Then you have your virtual or software interfaces. Virtual basically is a software interface, and these are the APIs. So these are also interfaces, but they are called application programming interfaces, which we will discuss a little bit more in next slides. So it allows software to communicate with another software. So it's basically, though we call it an API, application programming interface, it's basically a software piece or a software code that does the communication. So you have web services APIs, library-based APIs, and class-based APIs. I think those who are doing a little bit of programming and coding know that there's something called SOAP, REST, XML, JavaScript. JavaScript is widely used, and Java APIs, and also for mobile, we have Android APIs. So an API or an application programming interface is basically a collection of software functions and procedures that is defined as a code that helps two different softwares to communicate and exchange with each other, as I said. So it's basically two softwares maybe embedded in two different devices or two different locations, use the capabilities of software itself to achieve the communication. So it has all these requesting, sending, and updating type of scenarios, and then sometimes referred to as a contract between information provider and information user. So client server, information provider, user, talker, listener, something like that. Then establishing the content required from consumer or the call, and the content required by the producer, the response. So these can be entirely custom or specific. Again, there is no hard and fast rule how you should do an API. Just to show you an example, again, I actually got, with due respect to all these people who have done these slides, thanks to internet, these are publicly available, but I actually mentioned the sources of these two. API is basically like if you go to a restaurant and if you order pizza or something like that, you use some sort of a method and you give your parameters like what flavors and things like that you want from the waiter or the cashier or whoever does that function. And then the cashier actually requests that from the kitchen, and the kitchen responds with the final product, and then it is actually responded back to you as the pizza. So you have user, and then the application, in this case, the kitchen, and the API, application programming interface, acts as the interface between the application and you, is the API. Same here, suppose you want to use a database for storing or some sort of a data requirement. and then these are your devices, and how you actually access this database. It could be hosted in a cloud environment, is through an API, application programming interface. So it's basically an interface which allows you to do some sort of communication, basically at application level, but more correctly using the capabilities of software. So these are some comparisons between the protocols and APIs. Protocol is basically the way or the method that you do the communication. So it is sort of independent, when though the system neutral standard, whether it is a de facto or de jure type of standard, like TCP/IP is a protocol. So you don't care whether the protocol is running on a Cisco gear or a Juniper gear or Huawei gear, or what is the underlying equipment, router, switch, which runs this TCP/IP, or it could be my laptop here. We really don't care. So it is vendor neutral and vendor agnostic type of standard for communication, if it is a communication protocol. Whereas if you take an API, we have APIs which are generic in nature, but very often we find APIs are very specific. For example, if you do web-based development or web-based advertising or something related to web, you can use, if you want to use Twitter as an application, the Twitter API is a very specifically designed API to access Twitter information, which is the Twitter API. So you cannot use the Twitter API to, for example, access the LinkedIn platform or a Facebook platform. So it's very specific to one particular application. It need not be like that, but it is generally like that. So if you compare the method, for example, you can do the transport communication using an email, snail mail, voice, smoke signals, suitcase in parks. These are some of the examples you often find in the internet. And that is the method, so that is the protocol. And API is something like the language used. For example, if you're writing an email, it could be written in English, so that is your API. And it could be a snail mail, it could be Sinhala or Tamil, that is your language. And then smoke signals like military speaking and suitcases in parks, the code names, etc. So this is how you compare the meaning of protocol and API. Both are required in IoT communication. So in summary, what you see is what I have written at the bottom of the slide is protocols carry the information which is encoded to a specific APIs. Right? So you'll understand that as we move forward. So two of the widely used APIs these days is one is SOAP, which stands for Simple Object Access Protocol, and then REST, Representational State Transfer. So one would say SOAP is a protocol, but we have SOAP-based interfaces, so SOAP-based APIs. If you want to compare, SOAP is like sending some information or data from the client to the server with using the SOAP standard, which means that you sort of wrap it using the SOAP way of defining that particular block of data. It's like an envelope where you put your letter inside, whereas REST is like you directly transport your data from the client to the server, or from the IoT device to the gateway, or IoT device to the cloud, or whatever. So it is basically like a postcard. So that is what normally in the industry that we compare. So SOAP uses XML type of messaging, whereas REST uses HTTP type of messaging in these communications. The comparison is like SOAP is considered more bulky because it uses the SOAP standard and could get a bit heavier in terms of the communication, especially in IoT. And REST it's very flexible, and it's like very straightforward way of doing data transfer. REST is sometimes referred to as RESTful in the case of APIs. So when a client request is made via REST or RESTful API, both it transfers a representation of the state of the resource to the request or the endpoint. So that is basically what REST and REST API does. So how it happens is that it delivered in one of the several formats via HTTP. So it uses HTTP, not XML. And the formats could be like something like JSON or HTML, Python, PHP, plain text. There are many ways that you can sort of use that format. And out of these, JSON is the most generally popular programming language to be used. It is language agnostic, and also it is very much human readable. Of course, it is machine readable as well. And JSON or JavaScript object notation has these JSON, so JavaScript objects, which is very much machine readable. So it's basically two parts, especially in the case of IoT, the keys like the location, temperature, or whatever the keys that you want to collect, and the respective value. So it's basically very simple notation that you can use in IoT communications as well. So this is an example where you can sort of use the communication from things like Amazon Web Services, right? So if you want to use, as I told you, like Amazon has a lot of prefabricated, pre-built capabilities in the Amazon Web Services cloud, the public cloud. If you want to, like Rajiv mentioned, that you often need to store your data, like you can use something like Amazon S3 to store your data. And if you want anything like API gateways, system entry level, those things are available, right? And on the other side, you have, if you are using REST as an API interface, you have your IoT devices, web browsers, or applications. You can use, you can pass your information just by simply writing a JSON text or JSON code, and use HTTP methods like get, post, put, delete, the basic ways of sending data from client to the server and server to the client using these methods. So it's pretty easy, and these are very much standardized. And when you, I think we are discussing how you can do like a very joyful or very successful IoT project as your undergraduate project, or maybe your master's project. So one of the things you can understand is that you can often use many of the readily available platforms, capabilities, protocols, APIs. You really don't have to start everything from scratch, but using these combination of capabilities which are available in the cloud, which are available in devices, in the case of sometimes in the form of sensor capabilities, actuator capabilities, programming skills, but you can combine all these capabilities and actually bring out something very unique in terms of IoT. So it doesn't always mean that you have to build everything from the scratch. If you want, you can, but rather you can actually use very solid capabilities that are already readily available in the market and also in the open source space to run your IoT project. So finally, before we wrap things up for today, I just wanted to mention this. This is from the ITUT document, which we mentioned I think on day one. The sort of how you visualize the physical world of IoT and the information world of IoT. the information world is logical, implemented on software. Physical world is the things and the devices that you can touch and feel. So you have devices and gateways, and the ones shown in dark or rather black circles are the physical things. So physical things can be connected to a device, and these can communicate like device to device type of communication, or through a gateway, or directly communication. And on the information world side, you can actually map all these physical world devices and things onto an information world virtual representation or an abstracted view of the physical world, which is your software view, right? So you can have every physical thing mapped to a virtual thing, basically like a digital twin or something like that, or the abstracted view of the physical device, how you control. For example, if I take the example of Rajiv's mass exploration, that equipment. So that equipment is so many million miles away from us, but we still control it from planet Earth. So possibly what we really have is an abstracted view of that rover, and also the sensors and all the other equipment connected to it, and you physically represent it, rather logically represent it in some sort of a software platform. So that is the abstracted view of the physical world in the information world or the virtual world. So this is very important in terms of also important in your projects, but also it is important if you really want to understand IoT and also to realize IoT through a project or through any application or something that that nature that you're trying to develop or trying to understand. So I hope that that makes some sense in understanding IoT a little bit deeper. And with that, I think we can move. If you have any questions and clarifications, we can move for the question and answer session. Thank you very much.
Now it's time for the Q&A session. Feel free to type in your questions in